All right, well, good morning. Welcome to day 2 of calculus COVID. Good news is I should be cleared by Friday, which means we can start back up on Monday. I'm definitely feeling better, so we'll just see if I can get myself a negative test. But we'll see what happens in a couple days. So today we're going to talk about more uses of calculus and specifically some things from physics. So for those of you who are taking the calculus-based physics right now, some of this might be things you've already seen. If not, it's coming soon. But well, to someone like me, it's not a surprise that we take time in calculus to talk about physics and vice versa, because that's why calculus was invented. It really was created to do physics. So they kind of go hand in hand. Calculus is definitely like the language of physics. It's one of the main tools. So I'm going to introduce you to some of that today. We'll also do some more on Friday. But that's the plan. Before I do that, though, let me just turn it over to you guys. Any questions about the homeworks or anything we've been talking about? Like last time when we talked about arc lengths and surface areas, any questions that came from that? All right, so I see in the chat, Juan requested 2.4, number 10. Let me go ahead and write that down and we'll go take a look at that. Anything else from the homework that people would like to see? All right, well then let me go ahead and hop over to our homework set and we'll take a look at 2.4, number 10. All right, computer's a little slow this morning. All right, so hopefully everybody sees my desktop so that you can see exercises 2.4. And let's go take a look at number 10 here. All right, so we have, let C be this curve, y equals e to the 1.9x plus e to the minus 1.9x over 3.8 for x is between 0.2 and 1.5. All right, so they gave us a graph of this curve, and the dots there represent the endpoints. And then it says we want to find the surface area of revolution about the x-axis for C. All right, so we're clear on the question. So let me just write this function down here really quickly, and then we'll see what we can do about finding the integral. Obviously, you might have some slightly different numbers on yours, but it should be kind of similar. So if we look at it, you'll notice that what this does, it makes it sort of like a horn of a trumpet as that revolves. So this is a three-dimensional image of that. So it says first find and simplify the square root of 1 plus y prime squared, and then find the surface area. All right, so we know what we need to do. So let's do it. Let me switch my sharing to whiteboard and we'll see if we can work this out. All right, so first we have y equals e to the 1.9x plus e to the minus 1.9x. That's all over 3.8. So they said go ahead and find y prime squared plus 1 and the square root and try to simplify that. Obviously, that's part of finding surface areas, because if you remember the surface area formula, it's going to be an integral of 2 pi r times arc length. And the arc length, that is the one that has the 1 plus y prime squared, right? Or if it had been x equals, we could have done it as 1 plus x prime squared and so on. But that's why they said, go ahead and find that first, because we're going to need it. So let's see if we can get it and try to simplify it a bit. So let's start just with the derivative. So y prime, this 3.8 that's on the bottom, that's a constant. So I'm going to go ahead and just bring that out.
Is this the homework for the lesson yesterday?
This is, yeah, this is 2.4, number 10. So there's our y prime, or the constant. So now let's get to the e business. So I've got e to the 1.9x. What's the derivative of that going to be? Of just the first piece. What's the derivative of that?
Is it just e to the 1.9x times 1.9?
There we go. So it's going to be 1.9 e to the 1.9x, because e to the stuff, e to anything, you just get it again. But then we had to use the chain rule. And so the chain rule, we had to differentiate what's in that exponent, which is just the 1.9. So the e to the 1.9x is just the standard derivative of e to stuff times the derivative of that stuff. Okay, so then we can do something similar with the second piece. That one is going to be minus 1.9 e to the minus 1.9x for exactly the same reason. E to the stuff shows up again, but then we need a derivative of that piece of the exponent from the chain rule. All right, so to simplify this a little bit, I'm going to take the 1.9's factor amount and divide it into 3.8. And so that gives me 1/2, excuse me, times e to the 1.9x minus e to the minus 1.9x. All right, so before I go any further, how do we feel about that? Any questions on the derivative there? All right, so now we need to square that thing, right? Because in the arc length formula, there's the y prime squared. So let's go ahead and square that. We're going to take this, we're going to square it. So y prime squared is going to equal, I'm going to get 1/4. That's my 1/2 times 1/2. And then let me go ahead and write this out. We have to take this and multiply it to itself. So I'm writing it out like that so we can see that we need to FOIL. Otherwise, it's really easy to forget that we need to actually FOIL here. All right, so when I FOIL, yeah, 1/4 times e to the 1.9x times e to the 1.9x is e to the 3.8x. When I do the outside and inside parts, so the OI part, I'm going to get this negative e to the minus 1.9x times a positive e to the 1.9x. Since those exponents are opposites, they add up to 0. So I get e to the 0, which is 1. So like the outside's going to give me -1. The inside's going to give me +1. Or sorry, not +1. Another -1. So that's the OI part. And then the last, I'm going to get plus e to the minus 3.8x. So I know that this is probably a little bit, use your rules of exponents. They're the same rules of exponents that you've ever used for anything. It doesn't change with the fact that this is e to powers. we still do the same thing. We add exponents together when we multiply, right? And so on. Okay, so this is 1/4 e to the 3.8x minus 2 plus e to the minus 3.8x. So that's the y prime squared. But now we need to add 1 to it. Okay, so if I add 1 to this, then do 1 plus y prime squared. That's all of this stuff. So let me just go ahead and rewrite all that. Plus 1. But now I want to try to simplify this a little bit. So I'm going to get a common denominator. That 1 is the same as 4/4, right? Which means I can combine these. So I still have my 1/4. If I add 4 on the inside, and if I add 4 on the inside, this becomes e to the 3.8x plus 2 plus e to the minus 3.8x.
All right, I have to go again. I'll be back.
Okay. So there's my plus 1. It's the same as adding 4 inside of that. So I know that probably felt a little bit strange, but well, that's probably the easiest way to do this. So now I need to take the square root of that. Well, here's where we're going to make use of something we just saw. Come back and look at this piece where it was negative. And so where I kind of drew the black arrow. And notice that what that was, that came from squaring the e to the 1.9x minus e to the minus 1.9, right? Just squared those. Well, the minus 2 came from the fact that we were subtracting. What would it have looked like if this had been a plus? If those had actually been added together when we FOILed, what would have changed? Like on that next line, what would have been different? Like maybe this would have been positive. That would have been positive, right? So if this had been a plus, everything would have been positive, which would have given us a plus 2, which is exactly what we have. So it turns out that this thing that we've got is actually 1/4 times e to the 1.9x plus e to the minus 1.9x squared. So in essence, I just factored. It's just you would never in a million years see to factor that. All right, well, now we're ready to take the square root, right? Like if we come back to the arc length formula, this is the square root of all that stuff. And so what that's going to give us is a 1/2. It's the square root of the 1/4. And then the square root of that stuff being squared is just that stuff. So if we go back to the box for that homework problem, you remember the very first box was simplify the square root of 1 plus y prime squared. This is what we would put into that first box. In fact, let me go ahead and jump back to that one so you can see it, see what I'm talking about. We'll come back here. right? So it said first find and simplify square root of 1 plus y prime squared. So that we put in the 1/2 times parentheses e to the 1.9x plus e to the minus 1.9x. But now it says go ahead and find the surface area. So let's just remind ourselves what we need. We need 2 pi r and the arc length. And we just got the arc length. 2 pi is 2 pi, but then we also need the r. And the radius of these little cross-sectional circles is going to be the y value. And the y value is just the function itself. Okay, so let's go and finish setting that sucker up. So let me erase some stuff here. We've done the algebra on this, we can get rid of it. The important piece is the bottom. Okay, so we'll go from here. All right, so let's start setting this thing up. So our surface area is going to equal the integral from, our bounds were 0.2 to 1.5. We need 2 pi times our radius. And the radius was the y value, which is the function. So we're going to have e to the 1.9x plus e to the minus 1.9x over 3.8. So 2 pi r times our arc length, which is this thing that we just calculated. So the 1/2 e to the 1.9x plus e to the minus 1.9x. And then our differential is a dx because we're moving in the x direction. Oh, goodness gracious. All right, so that's what we need to integrate. I'm definitely going to simplify a bit because I've got some 2's that cancel. The pi over 3.8, I can pull that out. So I'm going to get pi over 3.8 times the integral from 0.2 to 1.5. And now I'm going to go ahead and FOIL out again. So the first is going to give me e to the 3.8x. Excuse me. The outside and the inside, they're both going to give me a 1. Same thing as we saw before. So plus 2. And then the last is going to give me e to the minus 3.8x. And so that's what I have to end up integrating. And we'll go ahead and get the antiderivatives, because when we're integrating e to the stuff, just like differentiating, we get the e to the stuff, but this time we need to divide. We basically just did a u substitution. The 2 becomes a 2x, and then the e to the minus 3.8x, we get that over minus 3.8. And at this point, I'm going to stop because I don't have a calculator handy, and this is really just a plug and chug. All right, but we got to the point now where we can calculate this surface area. Whew. All right, so let's just take a second here and let me open it up for questions, because I'm sure there are probably some questions here. What can I help clarify? Nothing? We're all good? And I forget who asked this. I think it was Vaughn. Is that the better one? Does that make sense?
Yeah, it makes more sense. Thanks.
All right, you're welcome. It's a lot of gnarly algebra, right? Like you think about everything that we did here. It's kind of ugly looking. It's bringing back some stuff we haven't seen in a while. And that honestly is the bane of most calculus students, is the algebra. So, all right. Before I quit screen sharing and everything, any other homework problems? Or was this good little review of what we were doing last time good enough for us to move on? All right, well, hearing nothing, then we're going to go ahead and move on. So a couple of you popped in while I was doing that example. So good to see you, Danielle. Thanks for showing up. And Edward, good to see that you're here today. And I don't know if Douglas is still here. I know he said he had to hop out, but I'm just going to go on record and say hi, Douglas. All right, so let's go ahead and start talking about more of the things that we can use calculus for. And today is going to be very physics. Okay, and I'm not going to really go into the physics a lot because this isn't a physics class. But I'm going to give you, at least I hope, enough of the basics of the physics for you to see where calculus gets involved and why we use it. And the key to all of it's going to be, every single example is going to be that somehow we're adding things up, because that's what integrals do, right? You think about all the examples we've seen so far, whether it's arc lengths or volumes or areas or whatever, we're always just adding up lots of really small things. Anytime that happens, that's going to be an integral, because that's what integrals do. All right, so I'm going to hop up to my whiteboard. So just give me a second here to transition, and you'll see me pop up in my other screen, and we'll go from there. All right, so I'll be right back. All right, so I am back, but up here at the whiteboard. So today, like I said, we're going to talk physics, and I'm going to start off with something kind of simple that in terms of what we're going to do with the calculus, and we'll kind of progress as we go. But the first example I want to talk about is actually calculating mass. So mass, just in case you're not really sure what that is, a lot of people will say it's the weight of an object, and that's not quite true. But in terms of our general real regular world vocabulary, that's what you want to think of it as. But it really is just a measure of, well, it's a measure of inertia. It's a measure of your resistance to motion. And that's why we think about it as weight, right? Like, excuse me, something really big, something really heavy, it's hard to push it. Something light is easy to push. And that's really what mass is. Mass is a measurement of that. Weight, the difference between that and weight is actually the force of gravity pulling you down. And your mass is the same no matter where you are in the universe. Your weight will be different depending upon different objects around you. All right, so that's the technical difference, but we can just think of it, it's your mass. Now, where we're going to use calculus here is when we're in a situation where we have an object whose density changes. So real quick, so we all know what I'm talking about here. First, density. This is the measure of mass per, and I'm just going to put here unit, because it can change. Give me 1 second here. I'm going to adjust my shade because I'm going to look too much outside glare. I think that's a little bit better. Anyway, so it's a mass per unit. So we can have mass per volume, and that's what we call volume density. You could have mass per area, that's your area density. You could have mass per length, it's a length density. All right, but it's always a mass per amount of unit. So if we have two objects that are the same size, and one of them is more massive, it's got greater density. So think about the classic, suppose you have just like a box here that's full of feathers, same size box full of rocks. Obviously the rocks are going to be heavier, they're going to have more mass, so that's got greater density. Okay, so that's what we're talking about. Now in the physics world, we use the Greek letter rho for density. All right, and so this guy, it's the Greek letter rho. It's spelled R-H-O, but we pronounce it rho, and it looks like a curvy P. It's not a P. Okay, it's not a P. It's a rho. It just looks like a curvy P. All right, give me 1 second here, guys. I got an issue with my screen. I can't actually see what's going on, which is a problem. All right. All right, sorry about that. All right, so we're going to use this guy rho. Now, where we can use calculus is where we have something that doesn't have constant density. Lots of objects do have constant density. It's the same weight distribution throughout, but there are a lot of things that don't. Like a great example is your body. I don't know if you've ever thought about this, but the weight in your body is not evenly distributed. There are parts of it that are denser than other parts, right? Think about all the tissues that make up your body. You've got bone and muscle and fat and skin and hair.
I'm back. What did I miss?
Okay, so Douglas, I can't like just stop and redo what we just did, right? So
Sorry.
No, I know.
Is this like the beginning of the?
Hold on 1 second. I appreciate you letting me know that you're back. And what you can do to find out what you missed is rewatch this video, because I will have it posted in the Canvas shell. All right. So all the different parts of your body have different densities. And so if we are going to talk about your density distribution in your body, it's definitely not constant. It changes. All right, now what we're going to attack is nothing nearly as difficult as the density of your body. In fact, we're not going to go three-dimensional. We're going to start first with just suppose that we've got a one-dimensional object that has variable density. Now, in reality, we can't have a one-dimensional object, but we can use this kind of technique for something that's pretty much one-dimensional, like if you had a string, a hair follicle, anything that's really kind of just got length to it that matters. So what we could do is suppose that we've got a density function. And this density function, it just depends on where we are. So I'm going to write here rho of x. So imagine we've got like a cable or something like that that's one-dimensional. And basically what this is saying is that if you were to look at different parts, it's going to have different density. And you can imagine in the real world, this is kind of applicable. Now, obviously in the real world, we're not going to do one dimension, but you got to be able to do this before we can jump to 2 dimensions, 3 dimensions. And you will eventually get there in calculus. All right, so basically here's what we want to think about is suppose we got this density function, and so each part has slightly different density. If I want to get the mass of something, if you look at this formula, density is mass times unit. If you want to get mass, your mass is going to be your density times that unit. And so suppose that this density function is just a linear density. So this is going to be mass per length. So that's what we're looking at right now. If I want to actually get the mass, I would multiply this density times its length. So suppose we've got this one-dimensional piece of string or cable or hair or whatever it happens to be. And I decided I wanted to find the density or the mass of just one little piece of it. The mass of this is going to be its density times its width. Right? Because it's density times length. So its mass would be its density times its width. Now, that would be for that little chunk, but maybe there's another piece, and I want to find its mass. Well, the same deal here. Its mass is going to be the density there times its width. And okay, well, I keep doing this. Here's another chunk that I want to find its mass. Well, its mass is its density times width, and so on and so forth. Well, if I want total mass, then what am I going to do? I'm going to add up all those individual masses. Hey, wait a minute. We're adding up lots of little things. That's your integral. Excuse me. So here's where integration is used when we want to find the mass of an object. If we've got its density, it turns out that the mass is going to be the integral from A to B, wherever our endpoints are. We're going to integrate that density function times its width. Well, the width is a little chunk of x, it's a delta x. But if we allow this to get infinitesimally small, that delta x becomes a dx. So there's a really simple example, a simple integral that we get of where we would use integrals in a physical application. But again, notice what we're doing. We're adding up things. We're adding up mass chunks. And so because we're adding up mass chunks, we need our integral. So let me show you an example, just so you can see it's not really that big of a deal, and what it'll look like when you have one of these homework problems. You'll see something that looks like this. You'll say something like, suppose I'm going to call it a cable, has density given by rho equals 1 plus x. So then find the mass of the cable if one end is at 2 and the other end is at 4. All right, so kind of standard, typical problem. All right, well, here we go. We want to find that density, or sorry, that mass. We need to integrate the density function over the bounds. So in this case, the mass is going to equal the integral from 2 to 4 of 1 plus x dx. I literally just put the density in there with my bounds. And this one's going to be fast, right? It's just power rule. So we get x plus x squared over 2 evaluated at 2 and 4. So when I plug in 4, I'm going to get 12. When I plug in 2, I'm going to get 4. And 12 minus 4 is 8. So the mass of this is going to be 8, whatever the units are. I'm going to do everything in metric, unless they have a problem that's specifically not in metric. And in metric, the masses are in kilograms. masses in our system are not pounds. And here's another issue that I kind of have with our society. We equate kilograms and pounds, and those are different things. Pounds are forces. They're not masses. Our system, you gotta love this, masses are in slugs. That's the unit of mass in our system, in the imperial system. Anyway, so 8, and I'm gonna go ahead and put kilograms on it. So if you want to get the mass of something, just integrate the density. Boom, no big deal. All right, so there's your first kind of application of integrals in a physical, in the physics world. All right, so the next one I want to show you is what we call work. So I know some of you are in physics. Have you seen work yet? Have you guys gotten to that point?
Yeah, we have in trig physics.
In the trig physics you did. How about anybody in the calc-based physics? Have you seen work yet?
We're like just getting into it, I think, kind of more like the forest, not so much work.
Okay, so work then is right around the corner. So I'm actually going to give you a little bit of a preview of what you're going to run into in physics. So work, this is another place where physics definition and real world definition are different. When I talk about something requires work, you think, okay, it's going to require some effort to do and all that. And that's not necessarily what we're talking about in physics, but in physics, work is defined as force times displacement. All right, now, for some of you might be going, you're using words I've never heard before. So let me kind of break this down a little bit for you. Force, a force, this is just a push or a pull. So these are the things that are pushes or pulls. So for example, right now, you guys are all experiencing the force of gravity. Earth is trying to pull you down. You also are experiencing a force pushing up on your body from the chair you're sitting on, the bed you're laying in, the floor you're standing on, right? Because it's pushing, it's keeping you from falling down. So it's a push that's acting on you. But anything that you can imagine that's a push or a pull, that is a force. Okay, displacement, that's just a measure of how far you've moved. Okay, so displacement is, I was going to write that, how far you've moved. And it could just be an object that's moved as well. Oh, and I just realized that you totally can't see that in the glare. Let me write it down here. All right, so for example, look at what I just did when I grabbed my eraser. So the eraser was sitting right down here in the bottom of the screen. I picked it up and I moved it up here. The displacement was that distance. I went from point A down here to point B up above. Okay, that's displacement. So it's just a matter of where you were. It's not necessarily how far you've traveled, because imagine I took this eraser and I start down on the bottom and I'm way out here and then I'm cruising around and I get to this point. Displacement is still that distance from the original point to the final point. It doesn't take into account how you got there. Okay. Anyway, so this is work. It's force times displacement. So take this guy again. For example, in order for me to move it upward, I have to apply a force. I have to push it, fighting gravity. If I know how much force I'm applying, I would just multiply it by that distance that I raised it, and that'd be how much work I just did. All right, or how about this? I'm going to start with it up here, and I'm going to let it go. So y'all saw it move, right? Why did it drop? Why did it drop?
Because of gravity.
Yeah, because Earth is pulling it down. So that gravitational force did work. It did work on this thing because it brought it from up here down. And if I wanted to measure how much work was done, I would just need to know what the force due to gravity is. And then I would multiply that by how far it fell. Okay, so that's the idea behind work. And for something like that, eraser falling just this little distance, you don't need calculus. Because if you think about these, the displacement is just what it is. It's how far it fell. But the force is always the same on that. Gravity doesn't change over that kind of a distance. So we have a constant force, we can multiply it. But what if your force changes? Let's think about, suppose we were in a situation where the force was actually changing as we were moving. So we're going to take an object, and in physics, all my objects are boxes. Like, I don't care what it is. This is a car, this is a cow, this is a planet. But we're going to move this a certain distance. So we've got our set displacement. But suppose that along the way, the force changed. Okay, so we're going to have a variable force. If I said, let's calculate the work, and we're just going to multiply force and how far it went. And I said, okay, so the force starts at 10 newtons, it ends at 30 newtons, then it changes along the way. And I said, calculate the work. So you go, okay, so I need to multiply force times that distance, but which force? It was 10, and then it was 30, and it had different values somewhere in between. I can't just multiply those numbers together. All right, so what we're going to do is the same kind of thing that we did before, where we break this into smaller pieces. So we have a variable force, but suppose I just look at how much force is done as we move the block this little distance. All right, I can approximate the force over that little distance time and multiply it by that distance to get an amount of work. And then maybe I go, okay, well, now that it's at that red block, let's move it a little bit further down the line. So maybe it's going to go to here. And I could go, well, let's calculate the work there. I've got a force over a distance. And every time, I just keep breaking it into chunks. And what I could do is calculate the work on that first step and add it to the work on the second step and add it to the work on the third step and add it to work on the fourth step and so on and so forth. And to make this better, I want those steps to get smaller to get a better approximation. So I'm going to want to add up lots of little increments of work. Well, if I add up a lot of little things, what do I get? An integral. Okay, so that's where the integral is going to come down here. Now, if you think about what we're doing, is I'm multiplying that force. So let's say that that force is some function, f of x. In fact, let me call it big F, because we tend to use big F's for forces. So I've got this variable force, big F of x. And on each step of the way, I'm multiplying it by a width, by an interval, which is going to be a delta x. So I'm going to add up a whole bunch of these, but I'm going to make them really small and have an infinite number of them. And the next thing you know, we've got an integral. So work as an integral is defined as the integral from A to B, so from start to end, of f of x dx. So when you have a variable force, if you know that function, then you can just integrate that from A to B to figure out how much work is actually done. And just so you guys know, like why we care about work is there's this thing called the work kinetic energy formula or relationship. And basically the more work that you do, the more kinetic energy you have, and kinetic energy is energy of motion. So think about this again. I'm going to drop my eraser. It starts speeding up. It starts getting what we call kinetic energy, and that came from the fact that gravity was doing work. So it's actually one of the fundamental things that we do. All right, so let me show you an example. We'll actually do a couple examples of work where we have variable forces. Okay, so the first example I want to talk about are springs. So springs, just good old, right? Spring, like what's our, in an old style watch, your suspension in your car, right? Any kind of spring. So you probably played with springs before. And what's kind of interesting about springs is the amount of force that a spring supplies depends on how stretched out it is. If you can imagine this, and I don't know if you've actually had this experience, but like playing with a spring, it's actually really easy to start like stretching a spring at first. But as you get it longer and longer, it gets harder. You got to apply more force. Same thing if you want to compress them. You have a spring that you're going to compress. It's pretty easy at the start, and then it gets more difficult. So the force that's being supplied by a spring is not constant. There is this law, it's called Hooke's law, named after the scientist who came up with it. And basically what it says for a spring is that the force for a spring is given by negative k times x. The x, this is the displacement of the spring. So how much you've stretched it or how much you compressed it. And then this guy k, this is just called the spring constant. And it's just a measure of the spring itself, like how hard it is to stretch it. An example.
Is that a negative K?
Sorry, go ahead.
Is that a negative K?
That is a negative. Yep.
Okay, thank you.
You're welcome. So that K, like here's an example of a spring that has a very small K, meaning it's really easy to stretch and compress. A slinky. I imagine you played with slinkies. Those are springs, but they're really easy to stretch, really easy. So they've got a very small K. An example of a spring that's got a large K would be a spring that's in your car suspension. If you've ever seen one, I mean, they're big. They're like this big around, that long, huge coils. And those need to have big K values so that as your car goes over a bump, it will compress a bit, but it helps like take all that energy and cause it to die out, right? Anyway, so every spring has a spring constant K. And then the negative, that just tells you that the force is actually pushing in the opposite direction of displacement. So think about this. If I take a spring and I stretch it out, what does it want to do? What would the spring do as soon as I let go? All right, and
It wants to go.
come back together. I love Danielle. I can see, I don't know if you guys see her, but also she just did this, she went. Right, but yeah, it's going to want to come back. So think about what I did. I pulled it away but that force is pushing in the opposite direction. And the same thing, if I take a spring and I compress it, what's it want to do? It wants to pop back out. So it's trying to move the opposite direction. So that's why there's a minus sign. So that's where this comes from. And it's been pretty well established that this is how springs behave. All right, well, let me show you an example then of a kind of problem that you might see that involves springs. All right, so here's your example. Let's just say a force of 30 newtons and you got to love this. Forces, their units are newtons, named after Isaac Newton. Yeah, I'll tell you what, maybe someday there will be a unit called the armbrust. There never will be, but that'd be pretty cool. I'm not gonna lie. All right, so let's say a force of 30 newtons stretches a spring a distance of 0.3 meters from its rest length. Okay, so if we've got a spring, we apply a force of 30 newtons, so we pull it with a force of 30 newtons, and it causes it to stretch 0.3 meters. All right. So here's what I want to know. Let's find the work needed to stretch a spring 1 meter. From its rest length. All right, so basically I'm just saying we got the spring, I stretch it 1 meter, how much work do I have to do? But I did tell you something about the spring, right? I told you that if we apply a 30 Newton force, it will make it so that we stretch it by 0.3. All right, so let's think about what we're going to need to do. We need to work. We're going to need some bounds so that we know like what our lengths are. And then we also need to have force. All right, well, since we're talking about springs, our force is going to be given by the F equals negative kx. So let's find that first. Let's find the force. So think about what we need. We need to figure out what K is. We need to know that constant. And that's where this first information is going to help us. So if we go back and we look at this, and I'm sorry about that. Let me try something here. Oh, okay, good. That glare's gone. So let's go with a force of 30 newtons. Stretches the spring a distance of 0.3 meters. Well, what I just gave you was a force and a distance, a force and a displacement. So we know that when that force of 30 newtons is applied, then we go a distance of 0.3 meters. Okay, so 30 newtons gives us negative K of 0.3 meters. So if I want to figure out the K, then I'm going to divide by the 0.3. And so 30 divided by 0.3 is 100. And the units on that are newtons per meter. And I know some of you are probably going, wait a minute, there was a negative and now that negative went away. I'm aware that that negative went away because really either the force or the distance is negative because K's are always a positive value. And I don't want to get into all the physics of how do we determine which one's positive, which one's negative. So just at this point, just smile and nod. Okay, so thanks, I see Danielle doing that. So like KV 100 meters. All right, so that means we're ready to actually do our work calculation. So our work calculation, we're going to be integrating 100x. And I'm going to go ahead and put the negative back in there because it's negative k times x. So we're going to have negative 100x dx. And now I need some bounds. And for my bounds, I need to know in terms of the displacement, where did we start and where did we end, right? So I said, I want to stretch the spring 1 meter from rest length. So that means I'm starting at 0. It's just at its regular equilibrium distance. And now I'm going to stretch it 1 meter. So that means I'm taking it from 0 to 1. All right, so that's what I integrate. So let's get that real fast. 100x, the negative 100 just goes along for the ride. X becomes x squared over 2. And I'm evaluating that at the bounds of 0 and 1. If I plug in 1, I get negative 50. If I plug in 0, I get 0. So I get negative 50. The units on these are joules, spelled Joules, named after another physicist. And that's the unit for work. Okay, so the spring is applying negative 50 joules of work. What? Hold on a second. So this is work done by the spring. It's doing negative 50 joules. All right, so first of all, what negative work? Yeah, negative work just means that that force is trying to restrict the motion. So think about what's going on. If I'm stretching out that spring, what is the spring trying to do? It's trying to stay at its equilibrium. So it's actually applying a resistive force, which is why it did negative work. Now, if we want to talk about how much work I had to do to stretch this thing out, I did 50 joules of work. I did positive work because I'm making it move in the direction that it's moving. I'm applying a force that's in the same direction. So again, like when I was talking about lifting this eraser up, I just did positive work. At the same time, gravity was doing negative work because it's trying to not go up. Okay, so that's the difference in the signs. But in terms of how much work is needed, I have to apply 50 joules of work to stretch it out, while the spring is trying to do negative work. And the reason that we got the work done by the spring is we were looking at the force from the spring. That negative 100x was what the spring was doing, not what I was doing. So there's a bit of a difference. All right, so basically for any one of these work problems, what we need to do is calculate a force. If we can get a force function or figure out how force is changing, then we've got a shot. All right, so before I jump to another example, any questions on this one? All right, so let's go ahead and look at another example. And this is going to be one where we're fighting gravity. All right, so here's this example. Suppose that we've got a spherical tank. And let's say there's got a radius of 4 meters. Is full of water. Okay, so it's going to be full of fresh water. And just so you guys know that the density of fresh water is 1,000 kilograms per cubic meter. Okay, so that's just the density of water. Salt water is going to be a little bit heavier. That's around 1,030. Air is much less dense. Air has a density of 1 kilogram per cubic meter, but that's how much a cubic meter of water would weigh. So you go 1 meter by 1 meter by 1 meter. That's going to be 1,000 kilograms. All right. In our system, it's like 64 pounds per cubic foot, I think. I don't know. Anyway, so that's the density of the water. All right. Now what we're going to do is we're going to pump this water out the top. And so here's my question is, how much work is needed to pump the water out the top? So like maybe this is a tank that we've got underground, a cistern or something. And so we just want to figure out how much work is going to take to pump everything out the top. All right, so here's our setup. So let's start by drawing a picture, just so we can kind of see what's going on and see if that helps us figure out what to do. So here's our spherical tank. We're going to be pumping the water. It's got water in it, right? So water. And we're going to be pumping it out of the top. Okay, so let's just first think about what force are we fighting? What force are we going up against here?
Gravity.
Thank you. Yeah, it's gravity. Right? Gravity is what we have to fight. When we lift things up, we are supplying work against gravity. So basically, we need to look at this and see if we can figure out how much work is being done by gravity. And that's the equivalent amount of work that we have to supply. Just like with that spring example, we calculated how much the spring did, and then we have to apply the opposite. Okay, so let's think about work due to gravity. All right, so if we want to think about, let's come back to that example with the eraser. And I want to figure out how much work is done as I move it from here to here. So let's think about what we need to know. We need to know its displacement. We need to know how far it moved. And we also need to know what the force is due to gravity. And so the force due to gravity, it's equal to what we call m times g, where this is your mass times gravitational acceleration. And on Earth, the surface of the Earth, gravitational acceleration is around 9.8 meters per second squared. So this guy, this gravitational acceleration is 9.8. So the force is going to be equal to 9.8 times your mass. All right, so that's the beautiful thing about gravity is that at least if we're going a short distance, it's always the same, and it's 9.8. Okay, so then the work, and let's go ahead and be good. We're going to make it a negative 9.8 times your mass times the distance that it moves. So come back to this example with my eraser. If I know what its mass is, I put it on a scale and I get the amount of kilograms. All I'd have to do to calculate how much work gravity did is I'd have to go, all right, I just moved it, half a meter. It's got a mass of 10 grams. Convert that to kilograms, multiply by 9.8, and I got it. And then I supplied the opposite, so I would have supplied positively. So it's actually really easy. It's mass times distance times the gravitational constant. All right, so if we come back to our picture, we need to think about this in terms of the water. We need to know the mass of the water, and we need to know the distance that it got moved. All right, now this is where the calculus is going to come in. The distance that the water is moving is not all the same. Like imagine some water that's right here at the very top. How far does that have to move to get out of the tank? Just a short little distance. As opposed to the stuff on the bottom, that water is going to have to move a greater distance. So it's going to depend. If we say how far does the water move, I don't know which piece of water. Different bits have different amount of distances. Okay, so here's what I'm going to do is let's think about all of the water that needs to move the same distance. And if we think about all of the water that needs to move the same distance, that's just going to be some horizontal strip. Okay, so let's actually think about just this strip of water right here. I gave it a little bit of thickness, but eventually we're going to get to infinitesimally. All right, so now all of that water is going to move the same distance. Cool. So if I want to find out how much work got done, I just need to find the mass of that strip of water. And that would be the same even if that strip was, let's say it was one of the really shallow strips. So like this little chunk right here. If I could calculate its mass, then I would just multiply it by the distance that it travels and 9.8. And I'd be good. Right? And the same thing if it's another one down low. Let me do one more in a different color, like purple. So maybe I want to look at this strip. Okay, so maybe you're starting to see the calculus. If I can figure out the mass of the green strip and multiply it by its distance, 9.8, and then I do the same thing for the black strip and the purple strip and all the other strips, then I could add all those together to get my total amount of work. I'm going to get a better approximation if the strips are thinner, until eventually I want them to be infinitesimally thin. I'm adding up an infinite number of them. Hey, that's an integral. Okay, so that's where we need to go. So let's just think about this then. We need to do two things. We need to make a measure of distance, and we need to know how heavy, how much mass is in each of these layers. If I'm going to do the mass, I'm going to use the density. I'm going to use the fact that it's 1,000 kilograms per cubic meter, and I just need to multiply that by its volume. So let's start kind of breaking this down. We have the negative 9.8. That's just going to be there. The mass, this is going to be a density times volume. That's how we're going to get the mass. And then, of course, we still need our distance, which that's going to be easy enough. All right. So I think probably the best way to do this is to put some coordinates on here and just start building the stuff. All right, so in terms of where I'm going to put my coordinate axes, I'm actually just going to put them at the bottom. So that the origin is at the bottom, although I can put it wherever I want. But I'm going to do it this way. I think this might be a little bit easier. And so let's just start with the bounds that we're going to need, like what the y bounds are going to be for our integral. Like where are all the different y's, or what are all the different y's where we have slices of water? Well, the bottom, of course, is 0. What's the top? What's the y on the top?
8.
Yep, beautiful. It's 8. Because remember, our radius was 4 meters. So that means the total diameter is 8 meters. So when I set this thing up, my y's are going to go from 0 to 8. Okay. So when we finally do our integral, it's going to be 0 and 8. Okay, let's talk about the distance that the slice is going to travel. So I've got my generic purple slice down here, right? And it's got a certain y coordinate, which is that right there. How far does it have to move? If I'm pumping it out of the top and I got to bring it all the way to the top, how far is it going to move? As a function of y. Well, let's just think about it. If this total distance is 8, but it's already gone the distance of y.
Would it be the square?
We don't need any kind of square root, actually.
Oh, then would it just be 8 minus y?
There it is. So the distance that it's going to move is this distance right there, right? That plus y is our total of 8. So our distance is going to be 8 minus y. So think about it. If we're at the very top and we've got a y value of 8, 8 minus 8 is 0. It doesn't move. if we're at the bottom with a y value of 0, 8 minus 0 is 8, it has to move the full 8 meters. And anywhere in between, adjust accordingly. Okay, so there's our distance. Sweet. Let me go ahead and put that in. So this is 8 minus y. All right, so now I got to get the mass of that slice. All right, so the mass of that slice, that's going to be the density times its volume. So let's see if we can figure out the volume of that little slice of water. What does that cross section look like? Can you picture it? What kind of shape would we see is that with that cross section? I've got a spherical tank, and I look at any slice of that sphere. What do I see?
A disc.
Yep, it's just a disc. It's a circular disc, just like all the ones that we saw when we did volumes of revolution. Right? A sphere is a volume of revolution. So we're going to get a disc here. If I want to know its volume, the volume is going to equal pi r squared, right? But I'm going to call it big R to not think of it as the radius of this thing. It's this distance right here. We need to know that radius. Well, that radius is just the x-coordinate. Right? As I'm moving up and down and getting bigger and smaller circles, the radius is always the x-coordinate on my circle. That's going to be pi x squared times its thickness, which is going to be dy. Right? So this is area times thickness, just like we did before with volumes. So let me go ahead and put that in here. We're going to have 1,000 times pi x squared dy. So there is our work for any one slice. But again, I'm sure you see what the problem is. I've got X and I've got Y, and I can't have both. So I need to have some sort of relationship or use some sort of relationship about X and Y. Well, that's where this circular tank comes into play. The X and the Y of the points on this circle are determined by the tank itself. All right, so let's get that relationship. You guys remember the equation for circle? That wasn't a question, that was a you remember. I hope you remember, right? The good old x minus h squared plus y minus k squared equals r squared, where h and k are the center of the circle. Well, we got that. The center of my circle, if I'm using this coordinate scheme, is at 0, 4. So if I put that in, I get x squared plus y minus 4 squared equals 4 squared. And check it out. I can solve that for x squared. So if I do that and I put that over here into my work for my one little slice, so I have the negative 9.8, I got the 1,000 pi. The x squared, I'm going to go ahead and square it and simplify just because I can. You end up getting 8y minus y squared. If you distribute, move things over, group like terms, blah, blah, blah. I want you just to trust me on this right now. You can do the algebra later. All right, but now if you look at this big, horrible, ugly looking thing, this is telling me how much work is going to be done to move one of the little slices. For the slice that's at a height of y. All right, well, cool. That's for one of the slices, but I want all of them. So now I need to add them up. And so here's where our integral comes in. So this guy, our total work then, is going to be the integral from 0 to 8. Right, because our y's were between 0 and 8 with this sphere. I'm going to multiply all this together. So I get negative 9,800 pi times 8y minus y squared times 8 minus y dy. And that's going to give me the total amount of work that gravity is doing. That's why it's negative. And we are going to have to supply the positive amount of that work to empty this tank. All right, so at this point, I think you see what you need to do. This actually isn't that terrible of an integral. A minus 9,800 pi you can pull out. And then inside, if you just distribute stuff through, right, you can FOIL that. You get 64y minus 16y squared plus y cubed. And notice that it's just power rule. It's actually going to be a really fast integral to do. There was a lot of work to get there, but once we were there, the integral itself is pretty easy. All right, so I'm going to leave this one here because again, we can get a value. The value itself doesn't really matter. But I want you to think about this in a real world like scenario. The fact that we're going to have to do work, right? The fact that gravity is doing negative work, so we have to do positive work, should make sense. Because imagine you have this tank, you want to empty it, you're going to have to do something. You're going to have a pump of some kind. You're going to have to supply some energy to it in some way, whether it's a mechanical pump, like an electronic pump, if it's a hand crank, something, right? We're going to have to do work. Now imagine that we had, instead of going out the top, we had just gone out the bottom. Now gravity would have been doing all the work. Because all you got to do, like, unplug it. If there's a little hole, then all the water is going to flow out. So use that to help you in terms of the pluses and minuses. Just think about, like, especially with gravity, if you were to just let it go and gravity takes care of it, that's going to be a positive work done by gravity. If you would have to do something, that means there should be a negative for gravity. All right, so I know that this one was pretty complicated, but I want you to think about how we broke this down, how we got to all these different things. I started just by creating my work, my force times displacement. Then I started breaking those, right, like in this case, the mass and the distance that's traveled, I broke those into their different pieces using my information. Obviously, it's going to be different if it was a different shaped container, right? If this hadn't been spherical, if it had been cubical or rectangular box, then our cross sections would have been rectangles. So when I go to calculate my volume, it's the area of the rectangle times the width. Right? If it was a different size, okay, the distance traveled might have been different. My bounds would have been different, and so on and so forth. But you can use what we already know. Break it into smaller pieces. And that's a technique I suggest with anything in calculus. When there are these bigger problems,
is break them down into smaller, more manageable pieces before going forward. Okay, so the homework, when you're doing the homework with forces, with work and all that, pretty much the forces that you're going to be given, if it's not just some function they tell you, but if it's something you have to figure out yourself, it's either going to be a gravitational force, something like this, or it's going to be a spring force. That's why I wanted to show you those two examples. But beyond that, you know, you could have gravitational force like real gravity force, like if we're talking about sending probes away from Earth, because then we can't treat gravity as a constant. But again, that's just okay, well, use your force formula. It's going to be some k over x squared in that case. Okay, and then integrate it. But it always comes down to finding force and multiplying by distance. All right, so I definitely have more physics examples I want to show you, but I don't really have time right now. If I were to start the next topic, it would go way beyond class time. So I'm going to stop here. But I do want to comment about a couple of things. On Friday, we're going to do this one more time. I am going in for a test today. We're going to see if I'm positive. I'm still positive. If I'm negative, then I can start coming back. But I just want to plan on we're in here on Friday. I don't want to leave it as a last minute deal. Okay, so on Friday, we'll be in here one more time. And hopefully that's the last time. So starting next week, we should be back. I'll be sure to keep you guys updated. But on Friday, we're going to be in here. Also, I know that we have a quiz set. We're not going to do a quiz since we're not together. I'm actually going to bump it. We'll talk about when that will be later. I haven't had a chance to really look at the schedule, but I know for sure we're not going to do it on Friday. Okay. But please continue to work on the homeworks. Continue to reach out to me either in office hours or emails. Because since I'm not there, I'm still available just in this alternate venue. So anyway, so with that, I'm going to go ahead and pause our recording, stop our recording, unless there are other questions. Any questions on this that you have at this point? And this is another one. I will have the video up later today. Go back and watch this. Watch it again. The more you see this, the easier it's going to become. Okay, so I'm going to go ahead then and sign off and wish you guys an awesome couple days. And I'll see you all on Friday.
Thanks, Bruce.